But yeah, so our next speaker is called Anindya Bhattacharyya, and yes, here he is to speak. You may want to get up slowly, as I think we've just.
This is turned up. This is turned up.
Okay, yeah, so it's done. Okay, sorry. Right.
Yeah, can we move that here? Okay, I thought I would really kind of talk in quite general terms about certain sort of basic ideas of category theory and topos theory, what these things are exactly. Really with the aim of giving people a bit of a feel for how it differs from set theory. The set theoretical ontology that Fabio laid out in Hearing an Event is very much based on, if you like, a foundational paradigm within mathematics of set theory that I think it's one can absolutely say was the dominant paradigm throughout the 20th century. It arose out of a series of paradoxes and contradictions and impasses that mathematics found itself in the late 1800s, and arose as a response to that, and acted as an incredibly powerful unifying force within mathematics for the next 50 to 100 years. And this is what we mean by the Cantor event, when David Hilbert said that in response to the controversies around Cantor that we shall not be expelled from the paradise that Cantor has created for us. Now, of course, all these paradigms eventually kind of get contested by new ones, and really in the 40s and 50s you started to see the emergence of what is called now category theory, and it emerged in I think it was amongst these new paradigms always kind of crop up in quite random areas of maths. You know, I mean, Cantor was working on some fairly, by contemporary standards, obscure questions about sets of real numbers, and essentially had to invent set theory to be able to grapple with this problem. And similarly, Eilenberg and MacLean and various mathematicians who developed category theory were working on their own little kind of, their own little specialism, their own little region, something to do with algebraic topology and homotopy theory. I don't know the details myself, but they came across this sort of what was initially, if you like, a formalism or almost a notational convenience for the purposes of organising some of the theorems that they were coming up with, called categories. And within the next 10, 15 years or so, this notion of categories, functors, and natural transformations started almost spreading like wildfire throughout the rest of mathematics, because other bits of mathematics have, you know what, that's the ideal way for us to think about these things too. So really by the 70s and 80s, there was a kind of avant-garde within mathematics that had all turned towards using category theory. We're using it as, if you like, the lingua franca of mathematics. It was beginning to displace set theory as the way you would, rather than writing things as, if you were to define a group, for instance, and this is probably those of you who did maths at school, you would get a statement like G be a set equipped with a binary operation dot such that blah blah blah, and statements like full G in G this holds. And the thing I want to draw attention to here is that in terms of the way these very kind of general statements are made in mathematics, you can see the mark of the set theoretical formalism, the epsilon symbol, the logical operator for all. Now, what started to happen is that because category theory was much more powerful in terms of unifying certain areas of mathematics, it started to displace that. Mathematicians started talking in terms of functors and natural transformations and adjoints and monads. And this kind of language slowly started to push out the kind of traditional set theoretical way of looking at things. In my own background, I did a maths degree in the late 80s and early 90s, and I did 1 year of postgrad where we did category theory. And one of the things that made me decide to leave mathematics is I thought, oh my God, I'm just going to have to relearn everything from scratch in this new conceptual kind of paradigm. So what I wanted to do really is just kind of talk a little bit about what that paradigm is. Now, we'll just review a couple of things about sets to begin with. One of the key points about set theory is that really it's all based around this one symbol, this epsilon symbol. It's kind of what the whole thing revolves about. And there are certain subtleties about it. For starters, it's not symmetric at all. You know, X is a member of Y is a totally different statement to Y is a member of X. And in fact, if you accept the axiom of foundation, the two statements rule each other out. You can't have both at the same time. But it is symmetric in one sense, in which the widgets that appear on the left are the same kind of widgets that appear on the right. They are both pure multiples. There's no asymmetry on that level. And that, you know, you do get slight variance of set theory where you get certain things that can only appear on the left. So this would be an entity that can be in a set, but can't have members itself. And we alluded to them earlier, these are called atoms. And they're impure multiples, so we don't allow them in ZF set theory. We cast them out of the Garden of Eden. You also get things that can only appear on the right. This would be, I'm going to use the letter C, you can probably guess what they're called. This would be something that can have sets as members, but can't itself be a member of anything. And that's what's known as a class. And typically, set theory gets around the famous paradoxes, Cantor's paradox, Russell's paradox, by saying certain things are classes, and that's what stops the paradoxes from working. And the way that mathematicians, working mathematicians, are taught to think about classes is that they are too big to be sets. Now, one of the things that very much struck me about the ECC, that is the wrong way to think about classes. The point about classes is they are inconsistent as multiplicities. They cannot consist, they cannot hang together in a unity in the same way that sets can. And I think, you know, that's actually a better way of understanding it, though it does involve kind of deprogramming a certain ideology that's hammered into mathematicians, that certain things are too big to be sets, and we call them classes. And God can see that they're sets, but we can't, us fool people. Okay, so the point here that I want to underline is that everything here is a pure multiple. It's if you like, there's been some talk about univocity of being, and in this sense, everything is set the same way. Now, category theory, in context, rather than having the pure multiple and the belonging relationship between multiples as its fundamental kind of concept, the fundamental concept I basically look at things is arrows. Arrows between dots. I mean, essentially all of category theory can be recast as dots and arrows. In fact, you can drop the dots. The dots are merely there for our convenience. They're kind of resting points as one arrow jumps off into another. And these arrows are typically given letters and names. And they go from a place called, and this is called the codomain. This is called the domain, sorry. And they go somewhere else, and this is called the codomain. And there are a variety of notations for this, and you will typically see something like this. F function, A to B. Now, of course you get functions in set theory. In fact, they're common across mathematics. Set theory would be completely useless as a foundation if you couldn't define functions in them. But functions have this secondary role. They are not fundamentally built into the ontology. They're something that kind of, pops out of set theory. There are things in set theory that play the role of functions. Whereas for category theory, this arrow, this notion of going from one thing to the next, is the elemental notion, and everything else is built on top of that. And this is one of the things that makes it kind of slightly hard going from a set theoretical way of thinking about mathematics to a category theoretical one, because all of a sudden you have to kind of, everything turns upside down. The things that you were considering to be secondary properties, like the dynamism of a function transforming one set to the next, you have to start thinking of as primary. And that's quite odd, because if you're thinking of the F here as primary, you're kind of thinking of the movement from A to B before you thought A and B. And that becomes an increasingly common theme in category theory, that a category, which is basically defined as a bunch of objects and a bunch of arrows between them that satisfy certain laws, we increasingly start thinking of the arrows first, and the objects kind of disappear from the equation. They just sort of fade into the background. And I want to talk a little bit about that, because I think it's quite a curious phenomenon, and it's one that's the obvious ontological consequence of category theory arises from this. Let me go into this, because it's quite a fundamental idea. But, okay, we've got in category, a category involves dots and arrows between them. And the key thing about them is you can compose these arrows. So if I've got a dot A and a dot B, and here's C, and G going between them, I can do what's called GF. And GF, it's written the other way around, because if you think about, if you had something living in A, say A was a set, you have little a as a member of A, F applied to A would be something in B, and then G applied to that would be something in C. So GF will be a function from A to C. And this is the idea of functional composition, that you have, your functions are basically kind of transformations, and you can chain them together, providing, and this is quite important, they match up at this point, providing that the codomain of F is the same as the domain of G. The target of the F arrow has to be the same as the source of the G arrow, otherwise you can't put them together. Now this is the point at which you start to see category theory rapidly departing from set theory, because one of the things that quite naturally arises from these is you can think of these dots as different types, different data types, different types of object. And the arrows, the Fs, as transformations from one type to another. So I could have a type of books and a type of humans, and the author function would convert, would give it a book, it would work out the author and spit out a human. And it would be something that has, it's a function, but it's typed. It has to have a book as an input, and it has to put out a human being as an output. Now, this kind of suggests a universe where, rather than having this single thing of the pure multiple that exists everywhere, everything is specified. Everything comes with type attached to it, and functions have their input and output types very, very well specified, and they can only be fitted together if they match. Now, this at first sight seems to put a great deal of constraints on mathematics. All of a sudden you have to kind of not just throw x's and y's about, but worry about, is this of the right type and does that fit in with this? But like with so many other elements of mathematics, what initially looks like a restraint turns out to be a blessing in disguise, because if we are rigorous about typing mathematics properly, a whole load of areas that we would normally get stuck on, it becomes much more tractable. I mean, problems in in computer science, typing has become a major area of the kind of avant-garde end of theoretical computer science. There are languages that insist on incredibly strict typing rules, very different to the normal programming languages that we might have played about with. In fact, one of them, Haskell, people say that the rules for the type checking is so strict that if you could actually get your program to compile without throwing an error, without saying your typing is wrong, it almost certainly does what you want it to do, because it's so strict that it's impossible to write code with bugs in. So anyway, I digress slightly, but this theme of typed versus untyped, I think, is something that arises out of this new paradigm of category theory associated with things like type theory, and it is very much something that contrasts with the untyped universe of pure ontology. Now, this business of and I'll just talk about a couple of the other basic axioms of categories. So we've got this kind of concept of composition, where we're chaining functions together. The other very important point here is that given every object, there is a function associated with it, which is essentially to do nothing to that object. You just leave it as it is. And this is called the identity of a, typically an ID A or 1A, there's a variety of different notations. And if we look at, if we consider another thing over here, the F here, this is the identity of B. And one of the fundamental axioms of category theory is that every object has an identity attached. In fact, you could drop the object entirely and just think of the identity of functions being the object. And this, again, is an area where category theory's implicit ontology starts to break with our mathematical common sense, that an object is essentially the same thing as an action, the null action of leaving that object alone. This is you're beginning to get a sense how this prioritization of actions over objects starts to kind of create a different way of thinking about things. And of course, these identities have certain rules. So identity of F on A composed with F is the same thing as F. If I do nothing to A and then do F with it to F, it's the same as I've done F. And on the other side, we have F equals, this should be the way I apologies. Let's sort that out again. So first we do the identity on A, then we do F, and that's the same thing as F. And similarly, if we do F, and then do the identity on B, which is do nothing to B, well, if we do F, we get something in B. If we do nothing to B, we get that same thing. So again, we get F. So you can see why these things are called identities. they act like ones in multiplication. 1 times 5 is 5 times 7, 1, which is just 5. Or 0 is an addition. If you add 0 to something, it leaves it alone. Now, these are this raises up something quite interesting. Suppose we have two objects, A and B, a function going that way called f, and a function going that way called g. And suppose, moreover, if we did f and then did g, well, what we did, we get a function from A to itself, and suppose that function was actually equal to the identity of A. So doing f and then doing g would just get you back where you were to begin with. And suppose also it worked the other way around, that if you did g and then did f, you get the identity on B. Essentially, you'd be in a situation where you could reverse. Any f and g would be kind of mutually inverse, reversible pair of arrows. And if at any point someone made you do f, say some bad person came and forced you to do f, and you didn't want to do f, you could just do g and get right back where you were. And you could do that several times, and it would just leave everything as it is. Really, we'd be in a situation where being in state A and being in state B would be more or less the same thing, because we can always kind of translate there and back again. This is called isomorphism. Right? The idea here, these things are called, these arrows are called isomorphisms if they have inverses, things that can go backwards too. And they always come in pairs. Isomorphic arrows always come in pairs, which is a point I think isn't stressed properly enough in category theory textbooks. You typically get an isomorphism, it's defined as a function f such that there exists an inverse called f inverse blah blah blah, and that kind of misses the point. The isomorphic arrows always come in perfect pairs, and you can see the symmetry of this diagram here, and that's also quite interesting because the arrow diagram is kind of symmetric as well. I mean, it's symmetric apart from the fact that I choose a direction to put the arrow in. Now, Wittgenstein once said that one of the later Wittgenstein things, the ones that people disapprove of, that when you point at an object, it's completely conventional that I mean that way. You could imagine a language where pointing meant you go from your finger to your shoulder, so I would be kind of pointing at the TV screen by doing this. And that there is this sense that the direction of an arrow is kind of arbitrary. And the way that mathematicians, the implications of that, the fact that, well, we have to choose a direction to put the arrow in, but it kind of doesn't matter which one. There are two alternative ways of doing it. Leads to a thing called the principle of duality. And this is, again, a very, very peculiar aspect of category theory that doesn't really have any necessarily analog in set theory. That every category theory theorem comes in two versions, one version and a dual. And you will see this in textbooks, that you get initial objects in categories, and they have their duals, which are called terminal objects. You get things called products in categories, and they have their duals, which are called sums or disjoint or co-products. Quite often you get the word co prefixing something to describe its dual. And a lot of very bad jokes in category theory based on this, by the way. So you'll see that prefix a lot. And you can see here that the symmetry of this diagram, it doesn't really matter which, I can turn it upside down, I can put the arrows the other way around. And what that tells you is the notion of isomorphism is dual to itself. It has a dual, but the dual is exactly the same concept, again, because the concept was symmetric to begin with. Anyway, we have this idea then of objects being isomorphic. And it's worth looking at in the category of sets. Where every object is a set of sorts, and every function maps one set to another. If we had two functions, two normal sets in the traditional way of thinking about it, A and B, and we could do this, we could go from A and B and back again. What exactly is going on there? Well, it's actually the same. It's actually what's happening here is Cantor's notion of things having the same size. If I can convert any element in this set into an element of that set and reverse that process, we have the same number of sets. I mean, Cantor's basic insight is that two things are of the same size if you can put them into one-to-one correspondence to each other. So, the fact I can do this tells me that I have the same number of fingers on each hand. And so, for two sets to be isomorphic in the category theory sense is the same idea as them having the same cardinality, having the same quantity in the traditional set theoretical sense. Now, of course, you get lots of different sets, all of which have the same size. I mean, I have 5 fingers on this hand, I have 5 fingers on that hand. I can put them in one-to-one correspondence. That means that I can probably translate back and forth between them in a quite canonical and straightforward way. But these are still 2 hands. It's not as if I have just the one hand. And similarly, while in set theory there are, given any particular cardinality or size, there are a whole profusion of sets of that size. I mean, let's take a very simple, with the exception, of course, of the void. There is only one set of size 0, which is the empty set. But if I looked at sets of size 1, well, given any set whatsoever, I could put it in, create a singleton of it. So there are as many sets of size 1 as there are sets in general, which is, of course, absolutely huge. It's the size of the universe. It's an inconsistent multiple. Yet, in terms of isomorphism, it's much, much simpler. There's all of these different things, X, Y, Z, whatever. They might all be different, but they're all isomorphic to each other. So we can always swap one for another. And this notion that objects in a category have kind of 2 levels of, if you like, the protocol of sameness and difference, the dialectic of sameness and difference, plays out in 2 quite different ways. One on the fundamental level of, are they the same object, which is, something that we would be familiar with in the set theoretical universe, where you have lots of different sets, and they can be the same size, but they can be quite different as sets. In fact, you've got a particular axiom of extensionality that governs when 2 sets are considered to be the same or not. So you have that level of what we might call object identity. Are they the same object or not? And then you have a slightly looser notion of object isomorphism. I say looser because any object, A, is isomorphic to itself because you can use the identity to go back and forth. So, identity is, if you like, a stricter version of isomorphism. Isomorphism is kind of, all we really care is what we can do with the object. We no longer care about what it actually is. And it turns out that, obviously for mathematicians, what you can do with something is much more important than what it actually is. And you see, with the shift from set theory to category theory, this notion of isomorphism starts to become much, much, much more important than identity. In fact, so much more important that category theorists consider something to be badly defined if we're even talking about object identity. There's a website you might want to have a look at called NCatLab, which is being developed collaboratively by mathematicians. It's one of the main resources on category theory on the web. And they actually have a term for definitions that talk about object identity. They call it evil. And they say definitions that use this are evil, and we avoid evil, which is it's quite interesting that it's a supremely ethical word is drawn in to really kind of bracket off and hide away this sort of layer of pure ontology. And this is the kind of interesting thing here, because by separating these two out, by saying we don't care about what the object actually is, all we care about is its isomorphism classes, the structure it has, the fact that you can do this and go back again, that gives us a certain clarifying power. It means we're no longer concerned about certain, if you like, implementation details. But it then becomes kind of unclear about what the relationship between these two levels is, or even if you need this level at all. And this really is where I think the ontological implications of this start really large. I mean, one of the things that I found very hard to wrap my head around in category theories is it's full of universal statements of this form that for all f there exists a unique map G such that blah blah blah. And it turns out that by unique we mean unique up to isomorphism. As in, that's the maximum level of specificity that you can talk about in category theory. I'll give a very simple example. We looked earlier at the singleton set. That's in the set theoretical world. How do we talk about singletons in terms of categories? Well, one of the interesting things about this set here is that I could have any set at all, Y, and there would be a unique map from Y to this set. And why is that? Because Y itself has got elements Y0, Y1, Y2, dot, dot. The map must send these elements to these elements, but, well, there's only ever one choice. You know, Y0, oh, it has to go to X, because that's the only thing in X. What about Y1? Oh, that has to go to X too. What about what? Oh, yeah, that's X as well. So, one of the features about singleton sets is that, given any other set, there is a unique map to that singleton set. And in fact, that actually defines singleton sets. If I had a set that had no elements, a void set, well, it would actually be impossible for me to create a map unless Y was void too. And then it would be fine. I'll just have the identity map on the void. So this doesn't have this uniqueness property. And if I had more than one thing here, x dash, well, given anything in Y, I now have two choices where I send it to. So there isn't a unique map, there are many maps. So it's only singleton sets that have this property that given any other set, there is a unique map to it. So one of the classic standard definitions in category theory is that a terminal object is an object X such that given any other object Y, there is a unique F. So object X such that for all objects Y, there is a unique map f from y to x. Now, suppose I had two terminal objects, x0 and x1. Well, by the very definition of a terminal object, there will be a unique map from x0 to x1 and a unique map the other way around. And if I compose those two maps, I would get the unique map from x0 to itself, which must be the identity. So consequently, any two terminal objects must be isomorphic. So this definition of a terminal object doesn't specify a particular object in the category, but specifies an object up to isomorphism. And that is basically as good as you could get. Essentially, it says a terminal object is in the category of sets, this will mean a set of size 1. But which set of size 1? Do we mean x in brackets? Do we mean y? Do we mean a? Do we mean void set in brackets? Not only can we not answer that question, in a deep sense we can't even pose it. The language of category theory prevents you from even making any sense of the notion that of which object in the isomorphism class it is. Now, at this sort of point you can start to see how category theory has very, very different ontological implications. It's a very different kind of universe to the layer of pure ontology. One way of kind of thinking about it or imagining it, it's an analogy a lot of friends of mine have used, is that you could think of pure ontology or set theory as the kind of machine code of the universe, and category theory is, if you like, the higher level language that we put on top, and that maybe one compiles into the other, but we don't really care about how it compiles. In fact, we design the high level language in a way that means we don't have to care about the implementation details and the way that the things are implemented. And I'll give you a quick example of why this might matter, or why this might be a good thing. If we take, we looked at this notion of a single set. So given any set X, we can produce a singleton, which is the set with one unique element that happens to be this. There are other things we can do with sets. Given sets X and Y, we can produce the ordered pair X, Y. In fact, given a set X, we can create what's called a diagonal map, which sends it to the ordered pair X and then X again. Now, oh yeah, and we could say do this twice as well. Singleton, singleton. Now, conceptually, these two things are quite different. This here is an ordered pair that happens to lie on the diagonal. It's an ordered pair of X followed by itself. This is the result of applying the singleton operation twice to a particular set. But the peculiar thing is that in most standard Zumorov-Fraenkel set theory, these two multiples are identical. Because if you think about it, ordered pairs, the ordered pair XY is defined by the Wiener-Kuratowski ordered pair definition. That you'll see that definition in most set theory textbooks as a definition of an ordered pair. And so then what is X comma X? Well, it is X comma X. Oh, X comma X, well that's just X, isn't it? Because extensionality means you can't have repeating elements. So we've got X. Oh, we've got another repetition here. So this turns out to be that. Now, I suppose one could say there's a certain kind of economy involved in this thing. We don't have to have two separate kind of notions. Our pure notion of set membership, we can use that to encode ordered pairs. But it's also the case that there's clearly no good mathematical reason why x comma x should equal the double singleton. And in fact, if we chose a slightly different way of encoding ordered pairs, and there are different ways you could choose, this wouldn't be the same. So you can see how, on the level of pure ontology, you actually kind of get these kind of little peculiarities and side effects that are, if you like, you can't avoid getting them, but they don't really capture what's going on mathematically. And one of the points about category theory is that you can, if you like, abstract all of that away. From a category theoretical viewpoint, well, this is just a terminal object, so it's the same thing as this. Now, that's an identification that kind of has some sort of sense to it. There is a sense in which all one-element sets are replaceable or isomorphic. But this is a quite different thing. This is the result of a pairing function. And so we can, if you like, create a mathematical language where the things, we don't get these accidental identifications on the ontological level that don't have any meaning attached to them. They're identifications that occur purely as a side effect of somewhat arbitrary choices that we've made. How do we exactly go about defining a pair, altered pair within our language? Now, and this is again one of the reasons why category theory has got a certain traction amongst mathematicians. The classic textbook is called Category Theory for the Working Mathematician. You know, there's this ideology of the pragmatic, practical working mathematician, not like these set theorists sitting around thinking about pure multiplicity, you know, what do they know about what it's like to be in the cold face of cohomology or something, you know. But it is certainly that I mean, I parody this slightly, but it captures something that mathematicians from all sorts of different disciplines have seized upon category theory with a certain eagerness, because the language that it comes up with and the concepts it comes up with directly mirror the ones that they use themselves in their everyday maths. Whereas the concepts that set theorists come up with are really quite bizarre and quite unique to set theory. You know, some of the weird constructions, like the von Neumann ordinal construction, or the natural hierarchy in being an event, where, you know, having insisted that X is a member of Y is not an order relationship, we then proceed to treat it as if it was and talk about transitive sets. And, you know, these are very, very peculiar things to wrap your heads around. If you're a set theorist, you have to learn how to think in these manners. But that skill itself seems to be completely unique to set theory. It doesn't seem to have, you know, set theorists kind of understand that, but other branches of maths don't care about it. Whereas category theory has this immediate kind of practical efficacy. There's another major textbook called Practical Foundations of Mathematics that is all based on category theory. And this, I think, is another kind of issue that crops up out of this, because it touches directly on the argument about the kind of the constructivist orientation in ontology. Category theory, type theory, and the associated new paradigms that are arising are pushing mathematics very much in the direction of this kind of constructivism. Partly this is because of the rise of new technologies and the sheer complexity of the task of trying to work out how to get all these different widgets to talk to each other through the cloud and the internet, despite the fact they're all running on different platforms and different languages, and, pinging messages each other and you don't know when the messages are going to arrive. To deal with that complexity, you need a rigorous theoretical base, and this kind of mathematics is supplying that. And it is becoming increasingly dominant within mathematics itself. That this, the mathematicians that I know were still kind of, are professional mathematicians. 20 years ago they were uneasy about certain aspects of set theory, and now they're dismissive of set theory. They say, oh, no one deals with sets anymore. We live in a pure categorical universe now. We don't think that the pure multiple has any special properties that give it some kind of, ontological prestige. A set, a group, an abelian group, a tree, a graph, all of these things, if you like, you have to have a strict separation between them. They're all of different types, but we live in a kind of democracy where all these different types are as good as each other. There is and that's a very, very, very different ontological world to the kind of austerity of the set theoretical universe. Now, I think over the next 20 years, the battle between that kind of set theoretical vision and this supremely pragmatic, supremely constructivist, supremely empiricist almost, practical working mathematician ideology of category theory is going to play out very, very strongly indeed. It seems to me that the wind is absolutely blowing in the direction of category theory. Friends of mine who started off interested in set theory, who then started to look at toposes, which are a kind of natural generalization of sets within category theory, then very rapidly stop doing anything in sets at all. They make sure that all their mathematics can work in an arbitrary topos and not necessarily ZFC. And if you think about the idea in logic of worlds, where we live with all these different worlds, each with their own logic, if you like, knitted into the fabric of that universe, what the kind of this new mathematics tries to do is present a kind of mathematics that doesn't care about which particular world you're in. That is, if you like, neutral or agnostic on those questions of fundamental ontology. Now, I have to confess, and I'll end on this point, that I'm in two minds about this, because on the one hand, I can see the power in Badger's arguments that notion of a sort of agnosticism, that democracy of objects, is supremely ideological, and I can see that the shifts in mathematics are being driven by the fact that mathematics is part of academia, which is a part of the capitalist industry now, and there is a lot of money pulling it in that particular direction. The links between commerce and computer science and mathematics and even the military now are much tighter than they were 100 years ago, and that affects things. But on the other hand, it seems to me that this new constructive mathematics is also throwing out a whole new set of concepts, a whole new set of ideas. It is, if you like, producing a new paradise for mathematicians, and that the Hilbert notion that, well, we shall not be expelled from this paradise, that holds too. So, as I say, I am kind of torn on this question, because while originally I started off my, studying set theory and was kind of interested in category theory as a secondary thing, and then started thinking of, well, maybe we could think of category theory as a layer that we put on top of set theory, so you have your pure ontology here and your phenomenology on top, or your ontology with the onto stressed, or your ontology with the logic stressed. There are different ways of thinking about this in theirs. I find myself increasingly pulled in the direction of, if you like, abandoning that pure ontological there completely, which sounds like I'm surrendering to the American pragmatists or something like that. But it seems to me that if we take the notion that philosophy has a mathematical condition seriously, philosophy has to be conditioned by developments in mathematics and in science. And this is certainly a development that is happening. I think it is going to be one that is going to dominate the next 2 decades. If you look at I might have mentioned this to people, but if people have Googled homotopy type theory, they'll come across, this has only really cropped up in the last couple of years, a possible rival foundational paradigm that explicitly says we are a rival foundational paradigm to set theory. We are based not on a pure universe of pure multiples, but on a typed universe where everything has a type and they all interact with each other in specified ways. And this is now making a pitch to be the new foundations of mathematics. And its big selling point, quite literally a selling point, is that the way, if you think about mathematics through this lens, the way that human beings do mathematics and the way that computers formalize mathematics can be brought closely together. And that's always been a big problem because you see the beautiful symbols of set theory, and no actual mathematician thinks in terms of the formalism of the. There's always been this gap between the way that we formalise mathematics and the way we actually think about it. And homotopy type theory, its big promise, is that this is a new way of formalising mathematics where we can bring these two things together. And thus the mathematician will become a kind of cyborg with a computer attached to them. It will no longer be this pure thing that we do in our minds with pen and paper like I've been doing here. So this, if what I'm saying is true, this might be the last time we'll see a presentation about mathematics involving pens and papers. But anyway, I've babbled on for too long, so I'll leave it at that.
So does anyone have any questions?
So maybe I'm misunderstanding something here, but it feels like maybe the interesting part of the ontology that you're doing with the category theory is listing the types in the first place. Because if you're giving the cardinalities and the isomorphisms of all these other things, the interesting bit is what the thing is rather than the structure that holds between them all. Maybe I'm...
there is a sense in which...
So it's like Newman's problem for structural realism or something like this, that a list of the structures that hold between all the things is great, but we want to know what those things are. So in this, it's great. I know what the isomorphisms are, etc. But I want to know what the identity thing is. Maybe it's...
I think one of the curious things is that once you start getting used to the isomorphisms, you stop caring about what the object is. I mean, one way of thinking of category theory is it's like a kind of high structuralism of mathematics. We no longer care about the positive content of the signifier. All we care about is its location in a differential network. I mean, to give you an example, I started off talking about groups, and groups were originally developed as what are called permutation groups. So you have an object and ways of transforming that object, and the elements of the group are transformations of that object. And then it took about 10 years before mathematicians realised we don't need to think about the fact that these are actually maps that are transforming a space of some sort. All that matters is the algebra of the way that the names of the maps compose. And that two groups that could come from completely different bits of mathematics and have, in terms of their identity, be quite different. If they have the same structure, they're effectively the same group. And Cayley's theorem is the famous theorem that jumps from one level to the next. That if you know Cayley's theorem. This basically says that given any concrete group, we can basically translate back and forth between concrete and abstract groups. So the certain thing that you think is really important of what the group actually is, actually you can abstract away from that completely. And interestingly, there's an analogue in category theory called the Yoneda lemma. There's a sense of the Yoneda lemma, which was developed like 150 years after this, is actually a kind of generalization of this for categories, and does the same thing. It basically says, I kept saying that with dots and arrows, but you can forget the dots. And the Yoneda lemma kind of formalizes that notion.
I may have misunderstood, but it seems to me that this is a fundamental idea, right? What you've just been able to just say. It doesn't matter what is inside whatever the object is anymore, it matters what's done to it, and then how concatenations of functions, of transformations, and that's what is also important for commercial universe as well.
Yeah.
Right? So
it's called duck typing in computer science.
Right.
If it quacks like a duck and walks like a duck, it is a duck.
okay, but you need the duck. You've got to have the type duck, right? So I was just thinking, as long as you've got your types, you're okay. But you do need to have the original. That was the original question. But you have to have this moment where you specify your
Identity
types.
appears at high level is what you're getting at.
Because
But you can then pull the same trick. Two types don't have to be the same. They just have to work the same way.
oh right, okay.
It's quite interesting. You start getting a ramified hierarchy,
Because
a Russell-style hierarchy.
So somebody thought, an analogue in the history of philosophy is that Aristotle can only secure the purchase of reason on concrete individual substances at the level of their definitions, right? And he cannot actually have any access to what is in the substance at the level of matter or anything, but it's at the level of the universal, like dog, that reason actually has access to it, and reason can do things, create judgments about dogs and so on, but the individuality of a particular dog is completely lost. It's outside
And impenetrable in a certain way. Yeah, there is a definite. There is something very Aristotelian about all of this, which is
I'm trying to get a question here. I'm not sure it's even going to take the form of a question. But it seems to me, I mean, I didn't have a clue until you told me about the implications of category theory, having read Logic in More. And the question, therefore, that comes to my mind has something to do with one of the conditions of philosophy, not really conditions of philosophy, if you see what I'm getting at. Now, de facto, what Badiou does all the time with the truth domains is choose. There are poets who are important, there are poets who are not. There are clearly political sequences that are important, there are political sequences that are not. One might have expected him to do the same here for the reasons that you've just given us, but he doesn't appear to have done that, or has he done that by virtue of the fact that category theory supplies logics of worlds, not a theory of being in the event? Is that a clear question?
Yes, I think it is. I mean, logics of worlds is an attempt to place category theory on and explain it in terms of logics, in terms of phenomenology. I think there's a lot of. I love the idea that logic no longer becomes something separated from mathematics, or ontology, but becomes woven into the structure of the world. I think that's a very, very good idea.
Is there an event of category theory in
I think there has to be a sort of.
But then in that case it becomes truth sequence, doesn't it?
I mean, but this starts to clash with the Platonism of the Canterbury things. So this is the question
You push that into politics, and it might.
I know. I'm a good red. I don't like the implication. you're saying.
No, I'm not at the moment challenging you. I'm trying to describe the problem.
Yes, and that is absolutely the problem.
Yeah.
Yeah. We might get the answer now.
I was really asking him the question, and I just wanted you to clarify the question.
Yes, some very simple remarks. First, I have written a book of category theory. I have not written a book concerning theory of sets. So category theory, I know really well. So at the level of mathematics conditioning philosophy, it was not by ignorance of the development of mathematics today that I made some choice. The second remark is about three cats and pure multiplicity. A tree is certainly a pure multiplicity, but a pure multiplicity is not by necessity a tree. Yes, that is very important. Finally, there is an ontological destination of multiplicity because it's an abstract form of everything, a more abstract form of everything. And so when you stay on the same level, pure multiplicity and tree, it's a joke. It's not a real argument. And after that, even in category theory, it's a necessity to distinguish between two arrows or a multiplicity of arrows. It's very different if there is only a finite number of arrows between two objects or an infinite. It's a set theory, in fact, inside, and in some sense as a basis of the part of a category theory. You know also that to escape some possible paradoxical conclusion, we must define at the beginning of category theory a universe, in the sense of Grothendieck. But finally, a universe is only a level of the cumulative hierarchy of sets. So I think there are many arguments to say that certainly category theory is a very important part of contemporary mathematics, and but from an ontological point of view, there is really a discussion. I think that the potency of category theory is, in my opinion, a descriptive capacity. There is something in category theory which can describe the form of a relation between very different objects and to compose a sort of configurations of objects, and where you are at the level of functors and so on, it's really the paradise of relations. Okay? But is the paradise of relations the paradise of being? It's a great question. And so we return to the very classical philosophical question: is the very essence of being as being relation, of the very essence being as such, is finally multiplicity or identity. Multiplicity, if you are on the side of Heraclitus, unity if you are on the side of Parmenides. And so it's not. I appreciate really your presentation, very philosophical of theory and category. But I think that there is many strong reasons to maintain that the level of theory of category and the level of theory of sets are not the same. That is, we cannot substitute for philosophical reasons. In mathematics, it's something different. For philosophical reasons, we cannot substitute theory of sets by theory of category in my conviction. And I propose an interpretation of that. I propose an interpretation that theory of set is purely ontological, that is, in some sense, the abstract theory of what is common to all what exists, to be a multiplicity, the more abstract point which is common to all what exists. And theory of category is a descriptive schema for the concrete world, in fact. In category theory, it's true that tree, multiplicity, and so on can be made in new relationships, but it's because there is something more descriptive, more complex in some sense, but in a very new form of complexity in a theory of categories. That is my position, and so how we can say that the goal, the thinking goal of the two are not the same. Even it's inside the development of mathematics. And the passage from the Cantor paradise to the categorical hell
Kew Gardens
is certainly a movement which must be explained even at the social level by some reasons which are not all very good. Orientation on pure relations, orientation, diagrammatic orientation. There is something in category theory. I know category theory. It's a very magnificent. But it is something which is near the contemporary world in some sense. Circulation, relation, communication, so on. Smartphone in some sense, between an object and another object, and so on. and if you love this world, it's okay. But if we have a sort of suspicion concerning the becoming of this world, maybe at the end you prefer set theory.
I have to think about that as a decision.
Okay, I mean, we're at time, so unless anyone has any massively pressing questions, is there anyone who has any?